In this video, I'm going to cover the instantaneous rate of change equation. So before I do so, I want to talk about the Common Core. And let's go back to Secondary Math 1. In Secondary Math 1, students are introduced to this idea of linear functions. And so a linear function, if we wanted to graph, for example, y equals 2x plus 3, here's our Cartesian grid. Our y-intercept is 1, 2, 3 up, and then we have a slope of 2, which means that we are going 2 up from this particular point, 2 up, and 1 over. So we end up with having a graph that looks more or less like this. Doesn't look as straight as I would like, but nevertheless the concept is there. But this slope, it helps define this linear function. And slope is defined by our rise over run. And then in Secondary Math 2, the big idea in Secondary Math 2 is quadratics. And a quadratic, when we graph a quadratic, this would be our y equals x squared. When we graph a quadratic, it makes a parabola. Now when we talk about slope with any curves, it's sort of meaningless because there are, for any curve, there are infinite slopes. There's here we'd have sort of a positive slope, down here a zero slope, and over here we'd have a negative slope. So it's sort of meaningless to talk about slope when it comes to curves. So we introduced this idea of an average rate of change. Average rate of change. And an average rate of change would be, our equation is, it's really like our rise over run, where we have 2 points. Let's say we have this point here and we have this point here, and I want to know what the average rate of going from one point to the next is. Well, that's just, it's just a line. And we can, in fact, this is called a secant line, but we can then, using this line, we can use the same concepts that we did back in Secondary Math 1. So this concept, so it's really our rise, again, our rise over run. And when we find our rise, these are just the difference between it would just be the difference between our y values over the difference between our x values. And of course we could figure out all the other, there's multiple average rates of changes on a curve. In fact, it turns out to be infinite. And in Secondary Math 3, some of these same concepts are rehearsed again, but it's not until calculus, before a new idea is introduced. A lot of times we talk about this as the gradient, or we could call it the instantaneous rate of change. So we have the instantaneous rate of change. And the idea is, so if we have some curve like, I don't know, like here's a curve, then we can draw what is called a tangent line. So I have some point right here. And a tangent line is defined by a line that goes through a curve through 2 points that are infinitely close to each other. They're so infinitely close together that there's only one way that you can draw the line, and it is this way. As opposed to drawing the line like this, where I'd also be going through the curve one time. So this is going to be our at this particular point, there's only one instantaneous rate of change line, and that would be this tangent line here. We could come up with one over here. That would be something like this. But this curve has infinite instantaneous rates of changes as well. Now I can use the same equation that we had above up here to derive the equation for the instantaneous rate of change. So that's what I'm going to do next. So I have my Cartesian grid, and I have some curve on the Cartesian grid, like maybe this. And I have, on the curve, I have some point that I want to find the instantaneous rate of change of. So we'll call this point, we'll call it A. And at A, this is some amount, some x value over, we'll call that x value over just x. And then, of course, there is some corresponding y value as well. We'll call this f of x. And then let's imagine that we have some other point. We'll call this some point b. And let me talk about why it would be sort of difficult to come up with if we're given one point, and by itself with the 1 point, let's say that 1 point is, say, 5, 3. And I want to come up with the instantaneous rate of change for this particular point. Well, using my equation that I had before this, y subset 2 minus y subset 1 over x subset 2 minus x subset 1, and I plug in the same point for my y values, that would give me 3 minus 3 over 5 minus 5, which would give me 0 over 0, which is undefined. So that method doesn't work. There has to be another way. So let's imagine that we have some other point, b, and that point b is a certain distance away. We'll call this distance right here, we'll call this h. It is h distance away in the x value, in the x direction from point A. So we're going to call this x plus h. And we also have a corresponding y value of this, in this case, we have f of x plus h. So we're going to use our equation now. So here's the idea. I have this, we're going to start out with an average rate of change. So we're looking at some secant line that goes through these 2 points. And then what I'm going to do is I want to find the limit of the slope between these 2 points as h approaches 0. So I'm going to bring b closer, so let's move b down here. So that would mean if I move b down here, then I would have my average rate of change here. If I continue to move b down where h is approaching 0, then eventually we're going to be, as b approaches a, eventually we're going to get this tangent line or the instantaneous slope at that particular point. So I'm going to use my equation of my slope of y2 minus y1 over x2 minus x1. My y values are going to be, so I have f of x plus h minus the other y value of f of x over the x value, so x plus h minus the other x value of x. And again, I really want to find the limit as h approaches 0. So this is going to be the limit as h approaches 0. Now we can see that x minus x, those cancel out, and I'm left with the limit as h approaches 0 of f of x plus h minus f of x over h. And this is the equation that I could use to derive any slope equation, any instantaneous rate of change equation for any graph, for any function. So let's start out with something that would be a little easier, some real basic function like, well, we've been talking about parabolas already. So our basic parent function for a parabola is y equals x squared. So let's call this, instead let's call this f of x. I just think it'll be easier for understanding it. Instead of calling it a y, we'll call it just f of x. So we have this function, f of x equals x squared, and this is going to give us some parabola. If we plug in -1, the -1 squared is going to give us 1, and if we plug in 0, 0 squared is going to give me 0. If I plug in 1, I get 1 back. If I plug in 2, I get 2. 2 squared is 4, so 4 up. So I end up with something like this as my parabola. And I'm going to find the slope equation for this function that will tell me any slope along this graph anywhere that I want, any slope, the instantaneous slope, I should say. So we're going to use this equation that we just got done deriving. And so I have the limit as h approaches 0 of f of x plus h. Well, if f of x equals x squared, then f of x plus h must be x plus h squared. And then minus, and f of x is our x squared, so I'll just substitute x squared in for f of x. And then that's going to be over h. Now, I have this x plus h squared, and I'm going to expand it, so I have x plus h squared becomes x plus h times x plus h. So that's going to give me, when I distribute, I'm going to get x squared plus x times h plus x times h plus h squared. Combine like terms, that gives me x squared plus 2xh plus h squared. I'm going to introduce this, so I'm going to substitute that, the expanded form, in for this factored form here. So I have the limit of h as it approaches 0 of this x squared plus 2xh plus h squared minus x squared over h. Now you should notice that we have x squared and x squared minus x squared. That's going to give me 0, so that's gone. So I have the limit as h approaches 0 of 2xh plus h squared over h. I'm going to factor out an h, so I have the limit of, as h approaches 0, of h times 2x plus h over h. H divided by h is 1, that cancels out, and I'm left with the limit, at the limit as h approaches 0 of 2x plus h. So as h approaches 0, I'm left with 2x. This is my instantaneous rate of change equation for the parent function of f of x. F of x equals x squared. This is the instantaneous rate of change, I'm sorry, you couldn't see that, equation for the function of f of x equals x squared. So let's look at our parabola again. I want to know what the slope is when this is my x-axis. What is the slope when x is 0? Well, let's plug in 0, and I get 2 times 0, which is 0. So my slope, that makes sense. The slope right there, the instantaneous rate of change right there, is going to be 0. What if I want to see what my slope is at, say, let's do 1. Well, I'm going to plug in 1. I have 2 times 1, which is going to give me 2. So I end up having a slope then at, so when x equals 1, the slope is 2. If I want to figure out what about when x is when x is negative 1? Well, we do the same thing, plug it in. 2 times negative 1 is negative 2, so the slope is negative 2. So I think I've marked up another graph, but I'm going to see if I can, I'm going to see if I can get rid of well, that's not what I wanted to do. Right, I want to know what the slope is. I'm going to see if it makes some logical sense. If my slope, I just figured out that the slope, when x is 1, that the slope is 2. Let's look at this graph and see if it looks like it. So when x is 1, does the slope look like it is 2? Does it look like the instantaneous rate of change at that point? Does it look like it's 2? Well, yeah, it does. You can see right here that we rise. We have a rise of 2 and a run of 1. So yeah, it looks like it. So if I have, oh, that was weird. If I have, what about when x is 3? So when x is 3, when x equals 3, then I have 2 times 3, which is 6. So the slope is 6. So we're going to see if that makes sense. So I'm 3 over, x is 3 over is the slope at that particular point, is it 6? Well, I'm going to have to see if I can drag this out a little bit. And, well, at that particular point, oh, that's not a tangent line there at all, so I need to change this so it's a tangent line. That's more or less, when x is 3, that's more or less a tangent line. Not perfect, but pretty close. And so from that point, do we have a rise and run of 6? Well, let's see. So it looks like we have a lattice point down here. So we have, from there we have a run of 1 and a rise of 1, 2, 3, 4, 5, 6, 7, 8. Well, that's way too high. So it looks like there's some, you know, sloppy work. It looks like well, that can't be a tangent line either because I can't cross the line. So I'm getting too sloppy with this. Let's see, is that better? Yeah, okay, so that looks, well, I'm not going to be able to get perfection, but I'm going to try to get as close as I can. Okay, so from my lattice point now here, we have a 1, 2, 3, 4, 5, 6. So that's more believable now that I have a slope of 6, an instantaneous slope of 6 when x equals 3. Anyway, I hope that was helpful for you, and have a wonderful night.